So what I like to you guys to do is help me go along. So we talked about water molecules and how water is essential for life. We have over 60% of our body made of water, right? The thing with water and understanding the chemistry is it's pretty darn simple once you get the structure. By the way, this quiz today is typical of how open book review quizzes will be. Notice, maybe one question you could have answered like directly out of your notes, but most of it was applying what was there, like the different properties. So you had to understand it in order to identify it. Does that make sense? It wasn't a straight example out of the book. Anyways, but water's water. It's H2O, no matter what state. Unfortunately, there's more than water in our bodies, and there's thousands of other different molecules. The cool thing is we don't have to memorize all of these different thousands of molecules to understand what they do and how they work. Because we notice that within these different molecules, there's different patterns that arise within their structure. And that's what this POGL was all about. That's what you were exploring here. And if you want to write really big on top of your POGL, structure. Okay, that was the point. We were trying to look at the structure of molecules, and we were trying to group the molecules. We were finding commonalities, common patterns within different groups of these molecules that we saw here. And according to the reading and the figure and some of the answers, most of the molecules outside of the water within living things can be divided into 4 main groups based on their structure, how they come together, and their elements. What are those 4 groups? And they're listed in the reading, and they're listed in the chart. Shout it out.
Carbohydrates, lipids, proteins, and nucleic acids.
Perfect. And so here's the deal. This is that part. Remember I did that little rant at the beginning because I went off kind of on 6th hour? Because these are the types of questions when I ask you and I tell you where it's found that people sometimes just stare at me. And I mean, like literally they could stare at me for like 3 minutes and we're just sitting here because no one's trying to find it. You know what I mean? So that's what I was referring to earlier. Questions like this, when you have that information, I'm going to show you it. And then if you're looking at it and you find it, and it was something I'm asking about, chances are it's something you need to know. So feel free to highlight it or something. Lipids, I don't know if I put them in the right order. It doesn't matter, but there's 4. Nucleic acids.
Protein.
Thank you. I had a mind fart. So there are 4 main groups, and the 4 main groups have, like, the molecules within each of these groups have similarities, things that they have in common that are different from the other groups. And that's what the questions, right? That's what the questions on the right side were showing us. Now, there are thousands of different combinations. They can come in any of these forms. There's commonalities, like for instance, number 9. Question number 9, it says something about what 3 structural groups shown. There were different structural groups shown that each of the proteins had. Do you see that question number 9 on your POGL? And when I went around and looked, I saw most of you guys had it. You saw that all 3 of them had what's called, you look at this part right here. Okay, this last part here where it said different groups. They all had an amine group, which is this, or some of you, I just told you to draw it, which is fine. All proteins have an amine group. They have a functional group and a carboxylic acid, which is the C double bond O, and then an alcohol group. Okay? So there's commonalities. Each protein, I don't care if it's just a couple of atoms or let's say a small molecule, just a couple of atoms, or bigger ones, you'll always see, oopsie, let's go this, these 3 groups, 1, 2, and then a C in the middle bonded to what they call a functional group. And that R could be a bazillion different things. There's a lot of functional groups. Actually, there's not too many, maybe like 20 or 23. But we don't have to memorize any of that. Okay? If you ever see a molecule that has NCC, these three parts, you know it's a protein. Likewise, okay? If I had a structure like this, remember I'm not putting the C's in, I could put the C's in if I wanted, but I'm shorthanding it. If I have this ring structure that looks like this, what would you guess it would be? What group of molecules? Look at your paper. What one do you think it would match up with? One ring with some hydrogens and maybe sticking off of it, maybe an oxygen here and there. But one ring, what would you say it is?
Is it carbohydrate?
It is. This is a carbohydrate. So what do you think this is? We can also do it like this. This is a different type of, okay, we can even start joining these. And here we go, we're having, this one's not on there necessarily, but it's a carbohydrate. So we start recognizing patterns. We can predict what category it falls in by noticing characteristics and patterns in the structure. Deal? Does that kind of make sense? I don't want you to memorize a bazillion molecules and what they are. I want you to just look at the structure as well as the elements. And that will tell you. First of all, what are the elements that I'm talking about, the 6 most abundant in life? In your notes the other day, we talked about 6 that there's a lot of in life.
Carbon, hydrogen, nitrogen.
Yep, we have that whole schnapps, remember? Okay. So I say the structure, the pattern, and the way it looks, but also in the elements. Also in the elements. So when you are looking at this, where are you? There you are. Do you see the very bottom one, nucleic acid? Do you see that P there for phosphorus? Okay. You're not going to find it necessarily in the proteins or lipids. Okay. That P, that phosphorus, is characteristic of a nucleic acid. So sometimes the elements within it can tell us too. So when you watch the biomolecules with Bozeman, it's going to go into it more. Just start looking, and if you read the textbook, looking and getting familiar with the patterns within them. Deal? Okay, so that is structure. There's also something, well, no, let's talk about structure for a minute longer. Let's talk about the backside of the pogo. Okay, when we have small single molecules, even larger ones, but we're going to start smaller, okay, like this carbohydrate right here. We can sometimes come together and form bigger ones, okay, and form bigger ones. So I think the example here, they had a glucose and a fructose, yep. It doesn't matter really, as long as it's a ring shape, it has an O in it. Again, I'm not drawing my carbons or my hydrogens out, but we have 2 small carbohydrates coming together in that top picture. Now, in case your chemistry is rusty on how to write out chemical reactions and equations, let me just show you this. And if you don't know it, write it down somewhere, either with those carbon chemistry notes or with the notes today. But in case you don't remember reactants, products, or this arrow, what it means. Reactants are what comes together. In math class, 3 plus 2, they can come together, right? They come together, they combine, and they equal a product. What's the product in this case? They make something. 5. Math, we're pretty cool on, right? Same idea here. We have reactants. We have stuff that comes together. When they combine, okay, it doesn't really equal it. We put them together. There's also a chemical reaction that happens to make them either bond or not bond. So instead of using an equal sign, we use an arrow. It's a chemical reaction helped these reactants combine. And of course, then we have a new product. It could be something bigger or it could be something smaller, but it's not the same as what we start with. So if you don't know reactants, products, or what those arrows meant, that's what that meant. I know some people had trouble with that model too because of finding the reactants and the products and what the arrows meant. Now, when we have one single unit, one small unit, what's the prefix for one? Give me a prefix for one.
Mono.
Mono. Okay, this is a monomer. Okay, this is Lego man here. Okay, I have one Lego brick. One brick. Okay, one brick. It is a monomer. It is one building block. Whether it's a monomer of a carbohydrate, a monomer of a protein, it's one molecule, one building block. Get it? We cool with that? Now we can take those monomers though, we can add them together and make a bigger molecule where they combine. Okay, so here's one. I am going to erase this in a second. My balance stinks. Okay. So now we can combine. I guess I did two glucoses instead of a fructose and glucose, but that's okay. The idea is that they combine, right? Now there's not just one, there's more than one. So what is a prefix for more or many? Especially many. It doesn't have to be many, but
Is that the poly?
poly, yep. And so here you're going to see poly. When we start building these together, when we start combining them and building them together, we now go from a monomer to a polymer. Now technically there's like, well, there's two, some of them are called dyes. But in fact, I think they said disaccharide here, didn't they, in a dipeptide or two. Oftentimes they don't use poly until you get 3 or more. But monomer and polymer is what I want you guys to know. Now, remember, when they come together, we can't just slap them together. When they come together, there's interactions between those electrons, and those interactions, reactions, action, just like in reaction, there is a chemical reaction that is going on. Okay? You don't just magically come together. So this is where I need to see a few of you. I need to see some volunteers to be monomers for us. I need some monomers to come up here, please. So I don't know, like maybe 4 volunteers. And at this point, Tasia, can you see? I think you can angle it so we can see over here. Because if anyone is absent and they want to see what's going on, this is a good activity to demonstrate the chemical reactions. So I need 4 monomers to play a game. I need 4 good students willing to be monomers for us. Okay, come on up here, Ashley. Okay, can you take your head down, please? Thank you. Okay, I need another. I'll start picking people. Ashley, I can go through. Thank you. Okay. Hey, I need another person. And go stand over by the round table. I need at least 3. Come on. Thank you, Caroline. Well, that's fine. Yeah, that's fine. As long as the 2 of you actually come down here. Oh, gosh darn it. You guys see what's happening? Don't show that part on. Okay, we're going to get in a line. Okay? Okay. So get close together. Right here. Perfect. Okay, so we have 3 building blocks. Remember I had those hexagons up here, those monomers of sugar, monosaccharides, actually, we'll find out. Okay, we've got our hexagons here, monomers. They're going to come together. Now they can get as close as they want, but they don't actually bond until a chemical reaction happens, until those electrons start mixing and stuff happens. But when that does happen and they become close, then we have a special type of reaction. And this reaction, these reactants are coming together. Yep. Okay, so we had our reactants. They are coming together. Okay, on the left side, they came together. The chemical reaction is occurring. And now you have one big molecule, polymer, and what was released? You guys are working. You don't say anything. What was released, you guys? You're doing all the work. You guys shout out answers. Water. Water was released. Stay there. You're still linked together. You're stuck. Okay, like glue. Okay. What is the prefix for water? Sorry. Yep, and then we'll turn back around one more time in a few minutes, okay? What is the prefix for water that we keep talking about? Hydro, okay? H2O is a formula, so it's hydro. Okay, if you build something, okay, because we built a molecule together with smaller pieces, we're looking at syn, the prefix syn. Synthesis. Like making music, you synthesize music. Okay? When you build something, it's called synthesis. Now, this was being released, wasn't it? The water was released as a product. When you take the water out of, like, fruits and veggies, what are you doing to that water? Or what are you doing to that fruit and veggie when you take out the water? Like, have you guys ever had these, like, snacks and it's like the fruits and veggies that, well, okay, let's think of fruits. They have been this. What do you call that when you take the water out, you put it in like the special oven to dry it out?
Dehydration.
Dehydration. Anyone ever hear of that word? Okay, if not, you do now. Dehydration means to out the water. Dehydrate. This is called a dehydration synthesis. Okay? Synthesis, you build it together, release water. So if you notice in part 2, you had water being released. It was one on the product side, wasn't it? Because in addition to that big molecule, there's also water produced. It's released from that big molecule, it's dehydrated, so it makes it like by itself. Does that kind of make sense for dehydration synthesis? And notice, right here. There you go. Dehydration synthesis. So on the flip side though, sometimes we are not building molecules, we want to break them down. Especially like when we eat those candy bars and we want to release the energy that's there, the sugar that's there. We want to take big molecules and put them into small molecules. So we need something to split apart these bonds. Oh my God. Yes. Okay, so what just split those bonds apart? You'll never forget this concept. Yeah. What did we just use to split that molecule apart? Anyone know what's in here? Or want to take a guess since I just squirted them with it? Probably not an acid, is it? What did I probably squirt them with?
Water.
Water. So I took water to split them apart. Water, split them. You guys agree with what just happened? Okay. We call that. What's the prefix for water?
Hydro.
Hydro. Hydro. And now, the second part of this is from the Greek lyse, which means to split open. Cells in your body will lyse open. They will burst open if too much water goes in. They get too big and they burst. To lyse, L-Y-S-E, means to burst. Okay? Or break apart. So that's where the L-Y-S for hydrolysis comes in. Water is used to break apart. You add the water to break a polymer into the monomers. So in this case, the water was a reactant. You guys cool with how to make bigger molecules now out of these biomolecules and break them down into smaller ones? You know the chemical reactions involved? We get out of here at 1:38, right? Okay, so we have about 4 minutes. You can go ahead and stop that.